Hey folks, welcome back. In this video we're going to look at charged particles in a magnetic field. So let's get going. Now we've already seen charged particles moving in an electric field, but in this video we're going to focus on charged particles moving in a magnetic field. Firstly, it tells us here that if a current flows through a current carrying conductor such as a wire, then a magnetic field will be produced around the wire. The direction of the magnetic field depends on the direction of current flow, and we can use something called the left-hand grip rule to help us determine the direction of this magnetic field. So for example, if you've got current flowing out of the page or screen, then we usually use a dot to represent this current. So you'll see here a sort of top-down view on our wire has the dot on the wire, the current carrying conductor. And if you take your left hand like this and point your thumb in the direction of the current flow, which would be out of the page or screen like so, then you'll see that your fingers will curl round in the direction of the magnetic field lines. So if we look at the top-down view here, if I've got my thumb pointing out of the page or screen, then my fingers will curl round in this clockwise direction, and that is the direction of my magnetic field lines. So it's a circular pattern for the magnetic field around a current carrying wire. And in this case, we've got our current moving upwards, so our thumb would point upwards and our fingers would curl round in this clockwise direction. On the other hand, if current is flowing into the page or screen and not out of the page or screen, then we can use a cross to represent this direction of into the page. So again, looking at our top-down view, we've got our current carrying wire there with a cross on it, which means the magnetic field is going into the page. So if we take our left hand again and point our thumb in the direction of into the page or screen, then our fingers will curl round in an anti-clockwise direction. And in this case, if our current's moving downwards, then we point our thumb in that direction, just like in this diagram, and the magnetic field is moving in this direction here. Now a handy hint, which is what we've just been using, is to imagine that you're holding the wire in your left hand with your thumb pointing in the same direction as the current flow. Your fingers will then curl to give the direction of the magnetic field around the wire. Now I'll just show you a quick simulation to help you understand this. So if you look at this diagram here, we've got a battery, a switch, and then a sheet of card with lots of compass needles attached. Right now the compass needles are all pointing north, but if we close the switch, you'll see the compass needles now all aligned to form this kind of circular direction, this circular pattern. And that's because if you think about the left-hand grip rule, the current is moving from the negative terminal of the battery here, down along here, up through the wire, back along through the switch and back to the positive terminal of the battery. So if the current's moving upwards, we could take our left hand and point our thumb in the direction of the current flow, which would be upwards, and that means our fingers are going to curl round in this clockwise direction here. So the compass needles are forming this circular magnetic field pattern. So we can think about these moving charges, these electrons, as moving through our wire, which is going to exert a magnetic field around the wire. And it will look like this. So there's our current flow or electron beam upwards and our magnetic field direction, which is circular. Going back to the notes, it says here that a wire carrying an electric current will experience a force when placed in a magnetic field. This is due to the interaction of the magnetic field produced by the wire itself with the external magnetic field in which it is placed. So we've just seen that a current flowing along a wire will produce a circular magnetic field around that wire, and we're then saying if that magnetic field interacts with another magnetic field, then you're going to get a force exerted on the wire. It then says when this happens, the external magnetic field pushes on the wire, causing it to move. And to help you visualize this, I'll just show you a quick simulation. So on the left here, we have a big horseshoe magnet, which will be our external magnetic field. So we've got the magnetic field lines going from north to south there, and we've got the symbol B here, which just represents magnetic field. On the right hand side, we've got a battery, switch, and some wires, and this is a simple series circuit set up. So when we close the switch, we know from the left hand grip rule that if the current's flowing up here from the negative terminal of the battery and down, then if we take our left hand and point our thumb downwards, our fingers will curl round in this direction of the magnetic field line, so we'll get this circular magnetic field. But we want to look at what happens when this magnetic field interacts with this external magnetic field. So if we place the wire in between the horseshoe magnet, then you'll see what happens here. We have all these distorted magnetic field lines, and they're all sort of bending around the wire here, which exerts a force on the wire itself. So the interaction of the magnetic fields wants to move the wire itself this way by this force F. Going back to the notes now, it says in the same way we can consider a single electric charge moving in a magnetic field. So instead of thinking about all of the electrons flowing along a wire this time, we're now just wanting to look at one of those electrons, i.e. a single charge. And we can say that this behaves like a mini magnet as it creates its own magnetic field. A charge will therefore experience a force if it moves through an external magnetic field, just like a charge experiences a force in an electric field. And we say the direction of this force is perpendicular to the direction of the current flow and perpendicular to the direction of the magnetic field. It can be found using Fleming's right-hand rule. and you might know this as the physics gangster sign. So here we have our right hand rule where you need to hold your thumb, index finger and middle finger at right angles to each other. So you'll see that the thumb is perpendicular to this first finger, and this first finger is perpendicular to this second finger. And the thumb is also perpendicular to this second finger as well. And we say that using the right hand rule for a negative charge like an electron, the thumb gives the direction of the motion, i.e. the force, which is often what you're asked to find the direction of in questions. So here we can try and remember that thumb represents motion. We also say the first finger gives the direction of the magnetic field, i.e. from north to south. So there's your first finger, your index finger, and you can remember that the first finger represents the field, first finger field, FFF. And lastly we have that the second finger gives the direction of current flow, i.e. the electron flow. So that's your initial direction of the electron that it's moving in to begin with. So you can remember that your middle finger, your second finger, represents the current. So the C within the word second there could help you remember that that's the current flow. We must note, however, that for a positive charge, the direction of movement is opposite to the direction worked out above. And if you're given a question with a positive charge rather than a negative charge, it's easiest to work out which way a negative charge would move first using the right hand rule, and then simply reverse this. You flip the direction. And lastly, just remember that the direction of current flow or magnetic field can be shown using the arrowhead coming towards you, which is like a dot inside a circle to mean out of the page or screen, and the back of the arrow or the cross to mean into the page or screen. So that's just a way of remembering which is which. So if you think about a cross, that's like looking at the back of an arrow as it moves away from you towards the page or the screen. So a cross represents into the page, whereas a dot inside a circle could represent the front of the arrow coming towards you. So that is out of the page or screen. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.